Cool. Should I use this, or does it matter?
Just that pocket one right
Ah.
there.
Sorry, there's the microphone. You can either do that or use the handheld microphone, whatever works better.
Hello? Oh, that's weird. Okay. Cool. So, hi everyone. I'm Arya. I'm from Edinburgh. This is, I think, the third formalization of WebAssembly that you've heard about today. So, I'm going to skip over a lot of details, obviously. But there are two main differences to the existing ones in this version. The first is that it's intrinsically typed. So, I think we touched on this a bit earlier. But rather than having a separate proof of each thing being well-typed, we just require that they are well-typed when we make the instructions. So it looks a lot like the spec. We're using different symbols, but in the context gamma, we can turn the stack delta into the stack delta plus a number on top, right? And rather than just storing indices into which label we want to break to, we need to provide a proof that the label exists and that the label has the type T. And then we constrain that if you want to use this instruction, you have to have the type T at the top of your stack. And that works similarly for instruction sequences. We require that you line them up between each instruction so that you can actually execute the next instruction. The second difference, which is maybe more noticeable, is that we represent our configuration differently. So in the WebAssembly spec, you don't, you have the same stack, which is an abstract machine, I think it's called, and that contains your constants and your instructions and these special fake instructions that represent control flow. Here, we have a separate operand stack, and we have the instructions that we're executing currently. And this lets us more easily write restrictions. So here, because we have delta in the same places, this requires that for a configuration to even be constructed, to be valid, it has to have an operand stack that's ready to execute the next instruction. So our configuration will always have the stack in the right shape. And then whenever we have control flow, where the stack is going to empty out and then change, if we enter a control flow block, we add it to this frames data structure, and we save the current operand stack and the rest of the instruction sequence, the continuation, and then we constrain the next version of the configuration. Whatever new instruction sequence we're starting to execute, we have to finish with what we're continuing with, right? So again, I'm skipping over a lot of details. The rest of the, the rest of the proofs are basically straightforward, defining your reduction rows, doing progress, which is especially straightforward because it's just what instruction comes next, right? The main thing to note is that obviously our reduction rows have to be different because this is not how they are written in the specification. They're a little bit uglier just because there are more fields that you have to deal with rather than just having everything in one place. Yeah, and because we're using a proof of progress, we get our evaluator for free. So this all gets figured out. It's not currently at the stage where we can instantiate modules, but it can evaluate things. So yeah, that's about all I had planned. I don't know how close I am to time, but if you want to talk to me about this, I'll be around after, or here's my email or my Fediverse, and yeah, thanks.
Great. And for our second speaker, let's have Marco. Oh, sorry. Actually, yes, questions first. Let's do just like 1 or 2 minutes for questions, so we'll try and be brief.
This isn't a question, this is a brag. People looking at this might think that Arya is a student and had a project where you put in hundreds of hours and so on, and this is the result of that project. What actually happened was Arya was a student in my class taught from my textbook, Programming Language Foundations in Agda, and there's a final project that's optional, which is there for students to show off if they can do something really good. And she went off and did this all on her own. I didn't say do WASM or anything, she just did it. and in a normal 10-unit course. So this is an amazing amount of work for an optional project in a 10-unit course, and I just want to point out what an amazing thing ARIA achieved. And
A very quick question here. How long did it take?
No idea. If you count loading Agda, if you count loading Agda, it took a semester. So
I think that's a natural place for us to rotate speakers, so thank you very much for speaking. Let's have Marco next. And I promise I did not deliberately do this. You'll see what I mean in a second.
Can I put the mic on you?
Yes.
Hold this first. Thank you.
Thanks. Yeah. Okay. So this is gonna be interesting. So so this project is mainly driven by two students that are working with me at Utrecht University. By the way, I'm Marco. I'm faculty at Utrecht University. So it's also about a intrinsically typed WASM. Basically, we are building a verified intrinsically typed WASM interpreter. So what is that? So that's an interpreter that operates on a well-typed intermediate representation. So that means that our syntax keeps track of all the invariants that all the types of the types of the things on the stack, or the type of the function in scope of a module and whatnot. And why are we doing that? Well, like the question that we're asking ourselves is whether types can lead to shorter proofs. And Philippa, thankfully, I already answered that question today, I think. You found that the intrinsically typed interpreter, the intrinsically typed, verified interpreter was at a fewer lines of code than the extrinsically typed one. The other side is about execution. So Conrad's interpreter showed that there are a bunch of tricks that you can use to make this interpreter faster. And we are continuing on that line. So we are doing this in Lean, which is nice. I think we have all been playing with proof assistant, and I'm not aware of any interpreter written in Lean. So Lean is a proof assistant that provides good support for dependent types and statics as well. We are using typed de Bruijn indices. So these are basically proofs that, things are in scope and have the type that you expect. And the other trick that we are using, or at least we're experimenting with in the interpreter, is to use continuations. So whenever our interpreter reaches some control flow instruction, is gonna build a continuation that will do something, do what the instruction is supposed to do with the things that it finds on the stack. So Lean Lean code can be executed efficiently. So Lean is a virtual machine implemented in C++. So we hope that compared to the type of code that you can get from other proof assistants, that will be faster. But there are some challenges with this intrinsically typed approach. So the fact that our intermediate representation is typed means that our runtime representation could have some of this information there. And this could cause unnecessarily overheads. So we're really interested in figuring out if we can completely get rid of these types at runtime. One thing in Lean that might help us here is that Lean has a special type for things that you can prove things about, a prop type. And these are guaranteed to be erased. So if we can map our dependent types into a prop, then Lean tell us this will be erased. So the way I see this project moving forward is that we'll have to figure out how to refine this dependent type into a prop type that then will be erased. So also, the main driving force here is Alex. He's a master's student at Utrecht University, and he started actually, even before this project, working with intrinsically typed representation. He built a interpreter in Haskell that is using GADTs and all sorts of type hackery, and now we're just carrying on these in the with Lean. So that's all I have. Thank you.
So I have an immediate question. When you're talking about intrinsically typed WASM, I'm taking that to mean that the definition of the WASM AST is intrinsically typed.
Yeah.
Do you ever expect to be able to erase those types, or are there different types you're talking about erasing?
No, I mean, like, I expect that, like, these types will be erased, yes. Or at least that's like, I mean, so like the way I see is that, yeah, like, this typed AST is like really good to do it for doing proofs. I mean, you can get, I don't know, like preservation for free. Like parts of the interpreter, I think, do benefit from yeah, like this type information. And I don't know yet if we're gonna manage to completely eliminate that, but yeah, like that's our hope.
Because I would, just to follow up, essentially the way we managed to erase all of our dependent types was because almost naturally in Coq, you pack all of your dependent types into a separate prop that's entirely off to the side, and it seems harder to play that erasure trick if it's interleaved with the AST. That's more of a comment than a question.
Yeah, no, I mean, yeah.
Like, two questions. One is, how do you generate these ASTs? You have a parser that validates as it goes, or?
So currently we have a parser that validates as it goes. We're also like thinking, yeah, like if we can start with the untyped AST, such as one, I think, from the, what's it called, the WASM specification generators that we heard today. Sorry, I forgot
the reference interpreter.
Yes. So, but currently we type as we go, yeah.
And the other question is, like, with this much more complicated type system we have now with GC types, so where you have subtyping, recursive types, and stuff like that, will that affect the strategy somehow? Will that make it harder for you?
We don't know yet. Currently, we are still at WASM 1.0. We're making good progress, so that would be like a nice test to see if this can be extended further. One thing that would be actually cool to do, actually looking at GC types and whatnot, is to see if some of these optimizations that Binarian performs could be, we could validate them and show that they're well typed with this type syntax.
So this is really for the whole audience, not just to you. But basically, okay, there's this bullet to bite, which is intrinsic versus extrinsic, beauty versus direct on the language. What have we just got this bifurcation? So the gang over there is not going to work with the gang over there, and vice versa. Or what do we do about this? Because I will be very bored if I have to start answering questions about this again in another talk.
My personal dream, and maybe Sam's as well, is that WASM DSL can produce both extrinsically and intrinsically typed definitions of WASM. And then we can all hug and live in harmony.
And then what should the Coq mechanization do? Which one? Do it back and forth?
Well, you saw the quote on the slides. You're meant to forget Coq has dependent types, right? Any other questions?
It's called research, Philippa. Right? We don't know what the answer is yet, and this is a step
Yeah.
towards finding out what the answer is, which is very interesting. I can tell you my one very preliminary result, which is that when I wrote PLFA, Programming Language Foundations in AGDA, I did it twice, once extrinsically and once intrinsically, and I found that the intrinsic code was the golden ratio smaller. So my slogan is that intrinsic typing is golden. On the other hand, if you tried to do type theory itself intrinsically typed, the answer is no one knows how to do it yet and make it actually run in a system like cubical AGDA or what have you. I'm working with Torsten Alkirch and some others trying to figure out how to do this. So that's too hard for us to do now. It's a research question. So we will just remains to be seen. It's very interesting to work this out, right? What is the best way to do it? We don't know what are the trade-offs. We're just learning. So there's much further to go, and it'll be interesting to see where we get to.
And is the same question there in the actual WASM language, or is it completely clear there that you want to be extrinsic?
Well, WASM wants to define the type system stuff, right? So
Yeah.
that's what you're saying.
Sorry.
So the question was, we can ask this question in abstract. For WASM specifically, is there a clear answer that one's better than the other? For now, WASM very practically wants to define its type system against an untyped AST. So that's the thing that naively led us towards extrinsic typing. We weren't thinking at the depth that the researchers here are, so maybe they have something to tell us. Sam. Find something else to say.
I was more or less going to say what Conrad said. So, I mean, I think this is a particularly interesting case to do some research in, because it's not your typical situation where you have just a statically typed term language where you're intrinsic all the way through. We need to be able to manipulate untyped code and validate it. And yeah, we can maybe make use of an intrinsic representation some of the time, but we have no choice but to deal with the untyped terms as well. So yeah, I think it's interesting.
But I mean, also one doesn't rule out the other. I mean, there is a correspondence between untyped, extrinsically typed and intrinsically typed. So I guess ideally you would like to get these transformations for free so that you can do the best task with the best representation.
Yeah, so then I declare the goal of WASM DSL is not just the untyped representation, not just the intrinsically typed representation, but the automatic derivation of conversion between them. We will definitely do this.
So actually, this is a question to both of the presenters so far. Did I open the mic?
Yeah. Sorry, I was trying to get over the camera.
Yes. So basically, I had some experience, on the Coq mechanization, and I was about to ask, when using the intrinsically typed approach, how what method did you come up with the initial typing derivation that you must fit into the initial interpreter? Because that was what I tried as well, and I think it has to be done via a type checker and plus some module instantiation typing results if you are starting from the module, or are you starting from the AST directly instead of the binaries?
Yeah, so as I mentioned before, we are currently doing type checking on the fly, which I guess has also drawbacks. One thing that we are actually considering doing is reusing the untyped AST automatically generated from the spec and basically type check that with an extrinsic or with an explicit type object, and then convert that into our typed representation. That would also be possible.
Any other questions or comments? I think that's a good place to stop then. So thank you very much.
Thank you.
And Maxime, I believe you're our third and not final speaker, because we also have Andreas.
Thank you so much. Thank you. Can I just stick the microphone? Yeah, real quick. So let's see. I love that, by the way.
Thank you so much.
Really good. Can you please like put this like onto your pants somehow? Possibly not into the pocket. Yeah, exactly. No, like you can stick it onto the pocket, but not into it. Perfect. Thank you so much.
Surely I need to plug in something. This thingy?
Yes.
Yes. It is now plugged in. Great, that is my screensaver.
Do you have an extended desktop rather than a mirrored
Maybe.
screen?
Perfect. So, hi everyone, my name is Maxime Le Goupil. I'm a PhD student with Lars Birkedal at Aarhus Universitet. I've now been working 2 years over there in Denmark. The first year before my PhD, I was a part of a group of incredibly talented people, Rao, Philippa, Conrad, who are here today, as well as Lars, Jean, and Aina from my home university in Aarhus, where we developed Iris WASM, which builds on the mechanization of WebAssembly in Coq and adds a whole program logic using the Iris proof framework that allows you to write proofs about specific WASM programs. These proofs are phrased in a typical separation logic language. So if I have this precondition which is phrased as a conjunction of different resources, then this is going to run safely and I'll have this postcondition with different resources when I'm done. And then if I then take this as a precondition, I can keep running and I'll end up with a different postcondition in here. If we have a look here at my example, you can see I'm calling functions like stack push and stack pop. So I'm imagining here that I have a library that implements stacks. And one of the important things that we wanted to have in Iris WASM is great modularity, and we wanted to show how we can reason modularly between different WebAssembly modules. And the way it will work here is that the person who's implementing the stack module is going to write proofs using Iris WASM of the way their functions work. And because we're using Iris, which is a higher order logic framework, they have a huge recursivity to write their proofs in the way they want. They can do things like completely hide the implementation of the stack behind predicates like this is stack predicate over there. Instead of my resources being, well, the stack is in memory at that place, I can just say, well, there exists a predicate is stack that relates WebAssembly values with mathematical stacks. And then me as a client where of the stack module, I can write a proof of my code where I am calling a function from the stack module using Iris WASM and that specification of the stack module. I can show that I'm going from having a stack that represents having a value that represents mathematical stack S to something where I've pushed the value 2 onto my stack. And so I can combine specifications of one module and another to then reason about different modules interacting with one another. If we look at the second part of my example, here I'm calling an adversary function that I've imported over there, and I'm imagining that I know nothing of this function. And what I'd love to prove is that after this call has returned without giving me any value, if I now try to pop from my stack, because I've never shared the stack X with my adversary module, I now get something that is 2 as in the value that I had pushed before. How am I going to prove that? That's the last feature of Iris WASM, is that we've written a whole logical relation. That means that we're now able to reason about unknown code. All we need to know is that the code for this adversary function types well in WebAssembly's normal type system, and then we get to know that the behavior of that code is not going to do things that are forbidden. Now, of course, in plain WebAssembly, if I want this to be able to work, I need to make the extra assumption that my adversary code does not have access to the function from my from the stack module, because obviously, if it was able to pop, it would be able to just guess arguments for the pop function and simply just interact with the memory in that way. Because like Amal mentioned earlier, in plain WebAssembly, if I have a memory, it's all or nothing. I either decide to share it or not. And if an adversary module has access to these functions, it's going to be able to interact via calling these functions. Even though I haven't shared explicitly this value x, in plain WebAssembly, the way memory accesses work is via use of I32 addresses, I32 integers interpreted as addresses, and that's something that is forgeable even if I don't decide to share it. This is where MS-WASM comes in. That was a proposition at last year's POPL where you would modify the semantics of WebAssembly to, instead of using I32 integers as addresses to access a heap memory, you would use handles to access memory in what we'd call a segment memory. So you'd have this form of enriched pointer that has metadata about exactly what areas of memory you were supposed to access. And that means that you can now share at a much finer grain because these objects are unforgeable, meaning that if I'm not explicitly sharing my variable x, an adversary module would not be able to have access to that value. And I can now share at a much finer grain. So what I've been doing now for the first year of my PhD is adapting IRIS-WASM to MS-WASM, meaning I have the full mechanization in Coq together with all the theorems we had proved that had been proved for plain WebAssembly, things like type safety via progress and preservation, partial determinism, as in determinism unless I'm doing, I'm using the few features that might introduce non-determinism. I have the full program logic that's going to allow me to prove proofs or theorems about the behavior of programs written in memory safe WASM, and I also have a logical relation that allows me to make proofs of robust safety in the presence of unknown code. These both projects so also allow us to reason about interaction of different modules, as I mentioned, but also interaction with the host, also reentrant interaction, and yeah, the hope is that now that we've introduced this tool, it's going to make the proposition of MS-WASM that was advanced last year at POPL much more precise and to show exactly what kind of guarantees we get from using handles in WebAssembly. Thank you.
Questions, please.
Thank you. So my first question, immediate question is going to be, are you going to, as I imagine, implement a different unforgeable pointer type that cannot be cannot be used to do pointer arithmetic? So so that's when you share those kind of pointers, the adversarial functions cannot use them to kind of figure out where your actual other address is.
Absolutely, that's exactly what MS-WASM does. So you introduce a fifth type to WebAssembly instead of just having I32, I64, F32, F34, 64. You now also have a handle type, which is a completely distinct object that is what you use to access memory. And then you have separate operations to allocate, deallocate these handles, perform some handle arithmetic. There are some restrictions on exactly what you're allowed to do, or actually you can do whatever, but once you've done it, you might not be able to use that handle anymore because the handle contains metadata about what exact parts of memory you were meant to have access to. So if you try to perform pointer arithmetics to now have something that points outside of the area that is specified by the metadata, any attempt to read or write is going to fail. And yeah, we suppose these objects to be unforgeable. That is achieved by adding an ID, and yeah.
Yes. So my next immediate question is going to be is there any mechanism here that say prevents you from prevent the adversarial function from storing a copy to its own global memory to be used later? Because it can like kind of duplicate the access you have given to the function?
Yeah, absolutely. That's a very good question there. So if you're interested, feel free to read the MS WASM paper from last year. They have a couple of subtleties that go with storing handles. You have to be a little careful how you implement that. But some mechanisms that are put in place are things like if you decide to free a memory, then the memories, if you decide to free a handle, the handle's ID now does not appear in the allocator anymore. So that means if someone else tries to use that handle, even though it's been deallocated, that is going to fail no matter where they got it from. So you still have mechanisms to deallocate the handle once you're done using it. But yeah.
So to give another piece of color to MS WASM as well, one way to think about it, and the way I thought about it when I was participating in the work, was it's a way of exposing cherry-like capabilities to a WASM level. So the point about ensuring you don't go outside the bounds of memory is exactly the agenda of a cherry capability. And the question Rao was just referring to there is about capability revocation. So you can also find literature at the cherry level on how to implement that and how feasible it is, just to give people pointers to some other work that might be relevant here.
So I guess, given that stack example, it's a great example to then extend your MS WASM work. Is that sort of your first? Because we were always having trouble finding examples. So is that your first port of call, or do you have other examples that you're thinking of? This will be the first thing to be looking at.
So we're still in the early stages of writing examples in Iris MS WASM, but we have implemented the exact same stack example we had in Iris WASM in Iris MS WASM, and we're currently exploring what can we prove in Iris MS WASM that we could not prove in Iris WASM, and this kind of example is exactly what we're looking at. Because if you're simply in plain WASM, there are some things that you can prove, some invariants about the way the memory of the stack module is laid out, that are going to remain true because anyone can only interact via the calls to push, pop, or all the other functions that the stack module exports. But nothing about the data because anyone can just push or pop anything by guessing addresses or providing whatever input to those functions.
So I guess just a sort of more general comment that whether it will be in Iris WASM or the Iris MS WASM, I imagine it's the same. There's this, it's difficult to find examples. And in particular, there's tiny things. And then because it's compilation target, there's huge things. But actually, for these sorts of program logics, what is right sort of WASM code to be exploring? And we don't know whether we're too early or whether it's never going to be that you get the standard libraries at the WASM level, or where is the place to start looking for this generic code? I think that's...
Yes,
if anyone can say it better than I just have to, but I think that's...
The big important code that you want to verify.
Yeah,
right.
Yeah.
We feel like probably a logical next step or a natural next step to this would be to try to automate a lot of this, because a lot of this can be automated, and when we've started doing that, then we can start actually working on examples that are much more realistic. But we've implemented the whole of WebAssembly 1.0, the whole of the industrial definition of the language is included in the mechanization, the program logic, the logical relation, both in plain WASM and in memory safe WASM. So we think, we're hoping that we're going to soon be able to do much more scalable, large, realistic examples.
Okay, one more question. Oh, sorry. No, I'm going to let Marco go because he's on it last.
Maybe an idea could be like if you have some, let's say, a memory allocator that you implement in C, and you could possibly like think about compiling it to MS WASM, and then you could prove that the allocator doesn't screw up and break memory safety, and that could give like, you could basically formalize what the secure allocator is in MS WASM and use some kind of robust memory safety guarantees. I guess that could be like a good application of this?
Certainly, yeah.
Okay, let's thank the speaker one last time. And now for our final thunder talk, it's Andreas, who's going to be...
Too many things.
Oh, do you have one of the cursed ones that doesn't adapt?
Yes.
You find it doesn't work.
Thank you. So one of the previous speakers had a Mac, right? So I kind of hope it
But with a
will.
direct HDMI connection, we can try.
Oh, okay.
You may need to email us.
That would be difficult, but let's see. Hello.
Wow, you have a really well-received.
How is it? Wow. Why is it? Okay. What happens if I present? Oh, it works. Okay. Right. So, last thing, I try to make it quick. This is actually something Conrad suggested, since this keeps coming up, like WASM 1.0, WASM 2.0. What do we actually mean by talking about it? And most people, I realize, in this community still are kind of behind the curve, right? And even being based on the PLDI paper, a lot of work seems to be based on the PLDI paper still, which is like 7 years old now. So WASM 1.0 is kind of what you know from that paper. It's roughly the same thing. Some minor syntax changes, some minor refactorings in the formalization, but that's the thing you all know. But that was like, 2018 when we standardized that, right? So that's a done thing in the past. Since then, we have not been lazy. We have done a lot of work, actually. So WASM 2.0 was actually a minor step. So the things that were added there were just a couple. Multiple return values, they actually were already in the PLDI paper, so that's probably not new. The big thing that was added there was vector type and instructions. So not particularly structurally complicated, but huge surface and a lot of irregularity. So as Sukyung pointed out, that makes it a bit painful. And then the kind of semantically more interesting thing was that we added reference types as a completely new kind of thing of value, like really opaque things that you cannot store in memory because you must not be able to observe bit patterns. So that might be pointers to functions or pointers to host objects. And that is kind of like a precursor for like what we now working on with garbage collection, stuff like that. And then there were various instructions that make like things like memory copy more efficient. They are not, again, not semantically interesting. They're just like a performance improvement. So that is also done. That was basically 2 years ago, we kind of, merged all this. So we have this notion of, like, you may not be aware of a live spec document now, which technically we still haven't really. Like, there's something with the W3C process that makes that very slow, but essentially you should think of the document being on GitHub.io/spec as being the current spec. And that has had these features for a long time, since like 2 years. Some of them even longer. Okay, but what we have been working like really towards is, I just phrase it as WASM 3.0 here. There is no real version number yet, but it's kind of like a nice way to phrase it. And that is starting to add more interesting features in terms of support for high-level languages, right? So what do I mean by that? So the first one is tail calls. The next one is taking the story with reference types further. So we now have like actually typed reference, so structurally typed references. You know what you're pointing to, like some function or some other thing. And you have a rich notion of subtyping and type recursion on that. So that really makes the type system much more like involved than it's currently. Currently, it's almost like trivial, right? You just have these 4 or 5 or 7 atomic types. And now it's like there's a lot of structure going on there. And based on that, the probably biggest feature we have added is garbage collection. So primitives to allocate something on an opaque heap So a heap that is completely separate from the linear memory. In the browser, it will basically be the JavaScript heap, but that, like, you can't really observe that. There's some heap, and the only thing you can do with it is allocate on it. And you can allocate tuples and arrays, essentially. And then you have reference to these, and that's where all these typed references come in. Multiple memories, Amal talked about that, or mentioned them. So that is really just kind of a hole we closed in the initial design, which we left there in very intentionally. So now you can have multiple memories in a single module. And that's, all these are, I put check marks there because they're basically done, right? All these features are done and just have to be merged, which is on me. The other thing that has been in the making for a lot is the threads proposal, which should more accurately be called atomics, because it doesn't really add the ability to create threads, but it adds instructions for atomic access to memory. And it comes with the whole like weak relaxed memory model and all the complexity of that. So this is also like a big addition to the semantics, at least. Another thing is that SIMD is now extended even further. So there's this couple of new instructions called relaxed SIMD, and that have this somewhat unfortunate property that they have implementation-dependent behavior. And the reason for that being that, like, CPU vendors simply can't agree, can't get their act together to agree on or converge on the semantics. And at the same time, people pushing SIMD really want to have cutting-edge features for their performance things. So we kind of were pressured to put that in. And then two more things which are not quite done yet, but will probably also end up hopefully in the next version we cut, which is exception handling. So you saw some of that on Daniel's slides. So it's kind of more or less like if you really squint ML style exceptions. So you define exception tags and you can throw and you can catch. And the other thing is with memories. So there are multiple memories, but we also are extending the address space by giving you the ability to declare a memory to have a 64-bit index. And that gives you full 64-bit address space. So yeah, all the things with the check marks are basically done features. You should consider them standardized at this point, more or less. They are at phase 4 of our elaborate process. And the other two are like almost there. I think we will reach like definitely this year. And there's more going on after that. I'm not going to talk through all of that, but like stack switching, Daniel talked about, and there will be continuations in one form or the other, either our proposal or some other variation. The sort of things of having shared state. So with atomics, you can just share memory between threads, but we want to generalize that to being allowed to share arbitrary references and globals and tables and functions between threads. So that adds some stuff to the type system, but also to the memory model, of course. And type imports, exports. Memory control is a bit vaguer at this point. There's like, this is the idea of having something like mprotect, maybe mmap, or some equivalent of that in the instruction set, because that keeps coming up. And there are more things I didn't talk about, smaller proposals that are in the making, but these are like the big ones you should be aware of. And right, so if you want to follow that, there's like this web page where they're all listed and you can see what stage they're at and how they progress. And so keep an eye on that. And this is the link to the live standard if you want. The spec, you should consider the current standard. And that is usually more further ahead than what the W3C has put out as its like document. Okay, so this just was, supposed to be an update on what's actually going on, so you're prepared for what's coming your way in the future. Okay, thank you very much.
What's your favorite feature, Andreas?
The best features are the ones we don't have to put in. Tail calls is probably, because it's so simple in terms of semantics, but has a lot of bang to it.
So this one that you say is the live standard, is that the very current version you've got, or the 2.0 version, or which version is that, or is it several and they're labeled in some way?
So currently none of the 3.0 features I mentioned are merged in yet, so it's 2.0 plus some fixes. But I will soon start merging things, and then it will be some part of 3.0, and incrementally we get there. And these versions are really just when we do an official kind of step of cutting the current thing as an official standard with a W3C. I don't know if that answers your question.
Is there somewhere else that you look to see the 3.0 stuff that's not in this yet?
So, well, none of that is in there yet. I have to merge it, but all the ones with a check mark could be merged anytime soon.
Yeah, I'm just saying, is there a public GitHub where you can see these or?
So I showed you the proposals link, so that has basically this one.
It's under that, okay.
There are links. So each proposal basically is a fork of the repo, which with the entire spec, with the specification of these features, like added. And now we
have to merge them to get spec.
Yes.
Okay. A very different question. You mentioned exceptions, and then we've got the continuation stuff. Does the continuation stuff subsume the exception stuff, or are they slightly different, or?
Like Daniel showed, the continuation stuff builds upon the exceptions proposal a little bit, so we use the tag mechanism they have for exceptions. But other than that, so our original design actually started out as a generalization of the exception instruction set. But for performance reasons, you actually want to know when you have a throw or suspend point, whether you need to create a continuation or not, right? That is a big difference in terms of performance. So you really want to at least annotate everything with, are you in the exception world or in the continuation world? So it ends up being two separate sets of instructions and types anyway. So
and they're mainly separate because one is much more performant than the other.
Right. So when you do a try for an exception, you don't want to create a new stack for that, right? It's just something you mark in the current stack. When you have a continuation, so with our cont new instruction, that is really under the hood allocating a new stack from the operating system, which is a much more expensive operation. And when you resume or suspend in both directions, you're switching between stacks, right? Which you don't do with exceptions at all. So that's why it really makes sense on this level to keep them separate.
Okay, thanks.
Two things real quick. Just want to mention. So the exception handling has suffered a little bit from almost shipping the wrong thing. So we're kind of recovering from that.
Yeah.
I'm responsible for fixing that. But you didn't mention profiles. Maybe you want to say something about that for this crowd.
Oh yeah. So right. So one thing which isn't really a feature in a way, but kind of like a way to annotate the spec is that we are adding or introducing this idea of profile. So there are lots of features here, and we have to support lots of different environments, ecosystems, platforms, some of which may not be able to implement some of these things, right? So for example, if you're running WebAssembly on a blockchain, you probably can't support threads. There's no way you can have non-determinism there. If you're running in an embedded system, you may not be able to support SIMD or GC because it's just like you really want a tiny runtime or tiny system, things like that. And the idea is that we potentially add this notion of profiles, which allows to define subsets of the language that exclude certain features. So there's the full language, but you can form slices in that language that exclude certain features, and that will be profiled. And one important one particularly is the deterministic profile. So that rules out all non-deterministic behavior, which we already currently have with NANDs, and with relaxed SIMD we're going to get much more of that. But if you're interested in actually well-defined semantics, you can say, okay, my environment's only running is implementing the deterministic profile, which removes some behaviors from the specification, from the semantics, essentially.
Have there been any visible adverse effects due to the increase in the scope of the language from 1.0 to 3.0? Like, for instance, has it entrenched existing implementations or existing runtimes because it's harder to include all the new features in a new one?
Yeah, I mean, it's certainly the case that there have been a lot of kind of smallish toy implementations initially, which are not really maintained, and they're definitely falling behind, and they're not maintained. I mean, they would probably fall behind anyway. But of course, it makes it harder for like developing a new implementation of WebAssembly. And there are currently like a dozen different ones, like the 3 major web engines, but also quite a few ones outside the web. And I don't know how many of those will like survive in the long term, because it might become too much of a burden to follow all these things. On the other hand, I also think that like the list of features I showed you here is probably like kind of a feature hump we are now getting over. It's all the kind of things we already wanted to do when we put out WebAssembly 1.0, when we designed it initially, but kind of consciously deferred because, yeah, we need to get something out quick. And now we are finally kind of, all these features are done and we can merge them in. And then after that, I would hope or expect there's a bit more of a long tail of other things following, but I hope it will not continue with that velocity.
Okay, thanks.
I think we're way over time anyway.
Yeah, that's a good place to stop. Thank you, Andreas. So I'll just end very quickly by saying thank you all for coming again to our inaugural WebAssembly workshop. If you have any comments about ways you think we should do this differently, or things you liked, or things you think we should change next time, please let me or Andreas know on Discord, by email, anything you'd like. But just apart from that, thanks again for coming, and please come back next year if we do this again.
Thank you, Conrad and Andreas, for organizing.
Yay.